Question 1 refers to children sitting on a seesaw, and the question uses the word pivot. So hopefully if you spot the word pivot in a question, you should immediately think about moments, even if the question's on an exam paper and not in a chapter called the Principle of Moments. So the first thing I'd do before I try to answer that question is I'd draw a picture of the situation. And there's the picture that I've drawn. So we've got the child of weight 200 newtons, 1.2 metres from the pivot. The seesaw is balanced by a second child sitting at a distance of 0.8 from the centre. Well, obviously for it to balance it's got to be on the other side of the pivot. And calculate the weight of the second child. So it's a really straightforward application. The question doesn't use the word equilibrium, but it says the seesaw is balanced, so it is in equilibrium. If it's in equilibrium, the principle of moments applies. If the principle of moments applies, the total clockwise moment must equal the total anti-clockwise moment. And if we're answering questions, we write that down. Total clockwise moment equals total anti-clockwise moment. But it's just a simple case of identifying what's the total clockwise moment. Well, of these two forces, this force W would tend to make the seesaw turn clockwise, and we know how to find the moment, force times distance. The reason that the seesaw doesn't turn is because this force is trying to turn it anti-clockwise, and we can find the moment of this, force times distance. Those two moments must balance because it's in equilibrium. Now to answer this question, those are the only forces we need because we're told that the pivot is in the middle of the seesaw. We're not told anything about the weight of the seesaw, but seesaws do have weight. But whatever the weight of the seesaw is, it won't affect the question, because the weight of the seesaw, we can assume that the seesaw is uniform, in which case the weight would act at the centre of the seesaw. And if the weight acts at the centre of the seesaw, it passes through the pivot. And if the weight passes through the pivot, it doesn't have a moment that we need to worry about. Question 2 describes a situation of a ruler supported at the centre of mass. Well, we'll assume a normal ruler, its centre of mass is going to be in the middle, and it's got various weights supported from it. And the first thing it asks you to do, which is probably the hardest part from questions like this, is to sketch a diagram to represent the situation. Now, even if the question didn't say sketch a diagram, there's no way I'd be able to do a moments question without first sketching a diagram. So here's the diagram that I would sketch. So the pivot's in the middle, it's a metre rule, so that's obviously the 50 centimetre mark. So it says that there's 3 newtons at the 5 centimetre mark. So 5 centimetres from the edge there, which of course is 45 centimetres from the pivot. It says that's 3 newtons. There's 2 newtons at the 25 centimetre mark. Well, 25 centimetres from the end is also 25 centimetres from the middle. And there's a weight W at the 80 centimetre mark. And of course 80 centimetres from the end must be 30 centimetres from the middle. So those are the forces. Now of course there are other forces acting as well. There's the weight of the ruler. If you think about it, it's a uniform ruler. The weight will act at the middle, straight down through the pivot, so it won't affect the moment. And then the other force that acts on the ruler, if we've got 3 downward forces plus the weight, we've got 4 downward forces. Why does the ruler not just go down? There's obviously got to be an upward force, so there would also be an upward force at the pivot. But again, because that force is at the pivot, it's not going to affect the moments. So unless you've got a question that says show all the forces, then we don't need to worry about putting that on the diagram. It only confuse matters. Now we've got to assume from the question it says the metre rule supports these forces. We've got to assume it supports them in equilibrium. So if it's in equilibrium, we know the principle of moments applies. So the total clockwise moment equals the total anti-clockwise moment. And thinking about the pivot, if that's where it's free to pivot, which force or forces would tend to make it turn clockwise? Well, this one here is tending to make the right hand side move down, so that's a clockwise moment. So we can work out clockwise moment, force times distance. But of course the ruler doesn't turn clockwise because there's something trying to turn it anti-clockwise, and these 2 forces here try to make it turn anti-clockwise. So we know that there are 2 forces giving anti-clockwise moments. There's this force times this distance, and there's this force. We've got to be careful here. The distance for this force from the pivot is that whole distance there. So apply the principle of moments. Total clockwise moments equals total anti-clockwise moment. Put the values in, we should get the answer for W. Question 3 is very much like question 2, it's the same situation, except that you swap over where the 2 Newton force acts and where the 3 Newton force acts. So you draw a diagram just the same as before. What the question doesn't say directly, but it does imply, is that it must be in a new equilibrium position, because otherwise it would just all fall on the floor. So we're assuming that you swap over those 2 forces. It says find the new distance of the weight W. So we assume that whatever value you got for W in the previous question, W keeps that same value, but in order for the ruler to stay balanced, you've got to move W. So the diagram, don't you cross yours out, you just do a new diagram. That becomes 2 newtons, that becomes 3 newtons. W will have the value you've just calculated, and that 30 centimetres is no longer the distance, it's going to be something new that you've got to calculate. So if it's something we're going to calculate, we'll call it X. Question 4 says you've got a metre rule which supports a 4.5 Newton weight at its 100 millimetre mark. So that distance from the end there is 100 millimetres. The rule is balanced horizontally on a horizontal knife edge. That just means like a sharp edge on a pivot. So the pivot, where is it? It says that's on the 340 millimetre mark. So it's 340 millimetres from the edge. So we've already marked off 100 millimetres, so let's mark that distance there, must be 240 millimetres. And that's where the ruler balances. Now we've got to think what other forces there are on the ruler. And the ruler has weight. Now in all the questions so far we've not had to worry about the weight of the ruler because it was always pivoted in the middle. But in this case it's not pivoted in the middle, so the weight of the ruler will have a moment. Now where does the weight of the ruler act? Well, it obviously acts in the middle, which is a 500 millimetre mark. So that's where the weight of the ruler would be. And I haven't drawn this to scale, but if that's the 340 millimetre mark, from 340 millimetres to the middle of the ruler must be 160 millimetres. So now we've got the relevant forces there. We're told the ruler's balanced, so it's in equilibrium, so we apply the principle of moments and we actually spend the time and the trouble to write it down. Total clockwise moment equals total anti-clockwise moment. We think, where's it pivoting? It's pivoting about there. Now there will of course be an upwards force there, but we're not asked to find that, and it certainly won't affect the moment because it's on the pivot. So the clockwise moment, force times distance, was to equal the anti-clockwise moment. That force times that distance. So we can use that equation to calculate the weight W.